In the last lecture, we had finished the axial point groups and showed you the three-dimensional axial point groups. And that was only using our new relationships between, n-fold axes in three dimensions, right? And so that set up some new rules. And like we've been saying about this class, that makes it kind of interesting. It's the beginning of understanding that, like we said, without any kind of Schrodinger equation or anything else, there's only certain kinds of axes at certain angles to each other that can exist around a point and create a set of motifs that are invariant under those operations. And so that tells us already there's some restrictions. And then now remember, these are all point symmetries, point groups. We haven't finished the point groups yet because now we have to put in what we're calling here extenders. So, we had extenders that we kind of put into the 2D, but we didn't call them that at the time. We just called them, other operations. Here we took just essentially our 2D space groups with a single higher symmetry rotation, and we, just moved them into 3D, and that was, a set of point groups right there. But then we applied our um, pretty much the Euler's construction and the law of cosines for a spherical triangle allows us to, get a set of equations that determines, the relationships of rotations about three axes in three dimensions. And now we're going to add extenders to that and explain our strategy for getting towards the final 3D crystallographic point groups. So again, we'll start with these axial ones and then we'll add these extenders. What are the extenders? Well, reflection and inversion are the extenders. And the qualification is that you can't change any rotational axis. So for example, if I have a rotational axis here and I want to put a mirror plane, because now we're in 3D, so this is a mirror plane, pretty much if I put it at any angle here, right, it's going to force this guy to be reflected, and I'll have some weird kink, and to have an axis continue, I'm going to create a new axis. And so that's not invariant to the mirror plane does not leave the rotation axis invariant, right? So you can see right away there's only two solutions. One is that I could put a plane vertically anywhere here so that the axis is in the center of this glide plane that I'm drawing here. So it's in the plane. So clearly that's allowed because everything will be reflected across here, but because this lies in the plane by definition, it's invariant. And then the other possibility is a new one. Now this one actually, well, I'll come back to that in a minute, but the other option, which is a new option, is I could put it in a horizontal way, because this also doesn't change it, because of course this just reflects about this point, and so I don't change the axes. So there's a couple of ways in which we can insert that are pretty obvious. Now, the green one here, I mentioned the words, I said the blue one's a new one. And that's because this green one, we're going to call a vertical operation plane. And that's actually kind of what we did before. Because if I look down on this structure, I've got the twofold, let's say I'm just calling it a twofold axis, the lowest symmetry, meaningful axis that I can have. And if I were to look down on this with my eye, again, looking down, this way, right, what I would see is that I would have a line passing through there, right? So this is actually the same thing. We used to call this a mirror plane, even though we're in 2D, and we called it a mirror line once in a while just to make sure you remember that. But you can see here that this one's pretty much just like the one we had before, and we'll see that we develop point groups that are dependent on the same theorems, right? Because, you know, the projection downward is indeed the same thing we had before. So this one is a new one, the other blue plane here, and of course, since the other one's called vertical, we'll call this horizontal. And that is new, of course, because we couldn't do that when we only had 2D. We could have if we wanted to have one of those things that, remember, allows us to do operations out of the plane. But of course, that would put actually things out of the plane again and not really relevant to 2D. So it didn't play a role there. Now, there's actually going to be um, a third operation, which is not very obvious, but let me introduce something now, which we're going to start doing in continue from what we were doing before. We showed these crystallographic projections, so we're going to continue with that. So remember that these, to show the three-dimensional point groups that can get kind of complex, we have these two stereographic projections. So these are spheres. Picture them as spheres, even though we're drawing them 2D. And so we show like, oh, well, if there's a twofold axis on the surface, you know, it still rotates about here. And then if I put a vertical mirror plane here, that would produce, you know, that would produce these guys here on the same surface. But then you can imagine if I put another mirror plane in the plane, that would reflect these guys about this great circle. And the way we're going to show that in the motif is that would put all of these guys on the other side of the sphere, right? So, you know, that's how we're supposed to think about this, is that the dark circles are on the sphere, that's the side that's facing us, where the open circles are kind of on the opposite side. But anyway, we also showed that, you know, if I had some sort of, and this isn't related to this one, so this is like, so ignore this now, and here's a fresh one. Let's imagine, and we'll see this, I have some higher symmetry thing in the middle, like hexagon or something like that, and some of the point groups, what I'll have is a lot of you know, twofold axes, you know, appearing here, you know, whatever this is. The point is to draw these guys around the outside here. And now you start to see that whatever this higher fold axis is inside, if we place vertical, we've been placing vertical planes, you know, there, or we place it on the great circle like we're just saying here, so it reflects things on this front surface to the back surface. But when you look at this, you realize that you could insert mirror planes in a new location in certain kinds of these stereographic projections, which would be a plane that passes, you know, through the sphere, cutting it, right? So it's, you know, we create a circle, you know, again in cross section, but it's cutting through here, the sphere. And this plane, you see, reflects everything about these guys. And you can imagine that'd be perfectly fine place to insert it. And that would produce a different result than if I insert it only along here. And so now that we're in 3D, we're going to just call this a special category. And I should have done a different color, not to confuse you with the green one over here, which is the vertical. So we'll make this magenta. And we're going to call this one a sigma d for diagonal. So we're not going to be able to apply that to many, because remember, everything has to reflect about this axis, and here in this particular case I'm showing you it does. So it can only be used in particular symmetries, right? But when it can, it gives us another option for adding extender. And so, if I wanted to complete our picture here, that's the only way I could put something not at an angle to the central, because see right here, this central axis, this is a vertical plane from respect to that vertical axis. So it's still like sigma v. But instead of sitting on other higher symmetries, we put it through a diagonal. And so that's going to be called sigma d. And then finally, we have the inversion, which we didn't have in um, in 2D. And probably the easiest thing to show you there is the motif stereographic projection. And so if I have, let's say, an object, a motif on the sphere, like a navel orange there, and what I do is let's place an inversion center here in the center of the sphere, right? Then what it'll do is it will produce, you draw a line from this point on the orange here through the center to the back side, and it will produce a unit here, a motif there. Now, the problem we have here is that one thing that these projections don't show, this shows it's on the other side of the sphere, but remember that inversion inverts everything. So this would be, let's say, right-handed, where this one would be left-handed, and there's no way to indicate that except that we'll just draw lines with L and R, just to remind you that the handedness is reversed when we pass through the inversion center and popping that image on the other side. So, and that's the inversion operation that we can add. And of course, I just showed you the simplest case, but we could have multiple motifs here passing through this inversion center. The last thing to discuss here on this slide is just that the translation is not an extender for our point group, right? Remember, point group means that everything operates around a point. These are all operating about a point. And so if you have translation, it takes this thing and then makes an infinite crystal out of it, or infinite lattice out of it. And so that is something that we're not going to do yet. We're going to do what we did in 2D, which is to develop the point groups first, and then we're going to have lattices that are compatible with certain point groups, but then we're going to place these guys in these lattices that we developed. So we're going to do the same. We talked about this a few lectures ago, but the strategy is once we complete the 3D point groups, then we will create the three-dimensional lattices, and then we'll bring the two together to make all the different three-dimensional crystallographic structures. Okay, now the map then for just finishing this part. So again, we're still focused on point groups, and we're adding these extenders to the axial combinations we've already derived. And so what I'm going to show you next is a table. And this table shows you all of the combinations. Now at the top, we have the 11 axial point groups that we developed. So see, this is, remember, 1, 2, 3, 4, 6. So remember, these are the simple ones where we just had the single rotational axis in the middle. Then we had said, okay, using our cosine A and our cosine B and our cosine C expressions, There are some solutions that create more complicated axial relationships than just having a single high symmetry axis passing through a sphere. We have the 222, the 32, the 422, the 622, the 23, and the 432. Now, it turns out we haven't done this one yet, and that's because the way we derive these, if we're going to be fair and show you some pedagogical development, we don't get this from the cosine A, cosine B, cosine C. This actually will appear now as we apply our extenders to things. This will become self-evident, and we'll derive that fairly quickly. But it actually is a new separate point group that, even though it's got this bar on top, it's actually a roto inversion that's unique to itself and belongs in here. It's not an extender. It's a unique point group on itself, and so we'll move it up to here. But we haven't done that one yet. And that's why it's not included here, because it's not an axial group. It wasn't derived through the axial relationships. The extenders are shown here. I've mentioned to you the horizontal. So this one is sigma h. The vertical, so this is sigma v. Diagonal, which is not as common, but it will matter for certain ones. And then, of course, our inversion, right? So the way we're going to develop this going forward is to say first, well, you know, our we've already done these, right? Because these are all finished at the top here. They are 3D crystallographic point groups by themselves. Before we go into the horizontal plane, the thing that's almost identical to 2D point groups, you can see here, it's behind this thing here, is this is 6mm. And all you do is put in mirror planes vertically, and you get the same analogy to our 2D point groups. And so what we're going to do here is we're first going to go down, jump down, and just quickly knock off the addition of vertical planes to these guys, because that's self-evident. We won't do these, but if you were to add vertical planes to these guys, you can see here that what this notation is telling us is that these are already present in other groups, meaning this produces the same thing, for example, as 2 over m, 2 over m, 2 over m. Now, we didn't talk about that yet because, it's over here, and I didn't do that yet. But I'm just telling you that we only need to consider these obvious ones straight up, because it turns out when I add vertical plane to all of these other ones, it produces things that are not unique compared to the way we're going to get into derive some of these other things. So when you look at this chart that I show you every once in a while, the only unique groups are going to have these projections, because every one of these says, like this unusual case, it says it's possible, but it's not crystallographic. This one is the same as 2 over m, right? This one's the same as 6 over m. So it's only the ones that you see here that have the projections that are actually going to give us the final 32 crystallographic point groups. And you can see that here, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So you can do that exercise yourself if you didn't keep up with me there. So that's just showing you that the unique ones are shown in this table. And that's what kind of nice, because with a quick view, you can say, okay, I know how I derive those. I'm adding these extenders. And the truth is, I see that when I add the horizontal plane, I pretty much get unique ones all the way across, except for this one in this new category. And then when I look at vertical plane, you know what? Some of these produce other things that already exist, but at least the things that are analogous to our 2D, all show up. And then there's the rare case where the diagonal can be inserted. You can't insert them in these because there's no place to put them. But then I can put them into these guys. And when I put them in there, in these three cases, I get three new point groups, but everything else is either non-crystallographic or not done. And then finally, we pick up a few stragglers because inversion center actually, what's interesting, and you'll see this, a lot of these mirror planes produce um, inversions at the center anyway. So a lot of these other point groups already have inversion centers that are induced by the extender. And so making unique ones is actually very difficult down here because, if we insert these guys first, they already get evolved this way. And so there's only a couple of ones that we didn't get from some other mirror plane insertion, and those would be 3 bar and 1 bar, right? And so we pick up a couple of stragglers at the end that need just a plug-in of a extender, where putting them into all these other things, they already actually have for inversion centers induced by other operations. And we're going to see that's a new combination theorem that in not next lecture, but the lecture afterwards, we'll go through. And that's why there are so many here that already exists here. And that's because, of course, we're going to find out that if I have a rotation and I add a horizontal mirror plane, I induce an inversion center anyway. And so that's why this is that way. So that's our mission. And next lecture, what we'll do is simply knock off these guys really quickly. And then get into a more unique situation of the horizontal plane and go through those derivations there. And we'll end up with these coupled with the inversion. And like I said, we won't spend a tremendous amount of time in these other areas because they're already been derived. They're non-crystallographic, but it would be a good idea for you on your own to say, I'm going to add an inversion center to here. Oh, it already has one, so therefore it's the same as blah, blah, blah. Okay? So you might want to take this and play around with it like that, just so you can convince yourself that these ones with the writing in them are either equivalent or non-crystallographic.